So last week we have discussed about the basic concept of logic gates, and we have discussed also about some complete sets. Complete sets, a set of gates is complete if we can implement any logical function using only the type of gates in the set. So for example, if we have none only, this is a complete set, or nor only, this complete set also, because using none only or nor, we can develop various other gates. And or not, on the other hand, is not a minimal complete set. Yeah. So minimal complete set is a complete set with no redundant elements. So for example, here using a NAND gate. So this is a minimal complete set. Using a NAND gate, you can make an AND gate like this. You can also make a NOT gate like this, or you can make also an OR gate using 3 NAND gate, not AND gate. NOR gate is also a universal gate, because using NOR gate, you can develop OR gate. Using 2 NOR gates, you develop 1 single OR gate. You can also make a single NOT gate. And using 3 NOR gates, you can make single AND gates. So this F value will be correct only if the value from A and B, the input value, are both correct. So these are some example of the chip, integrated circuit that is available in the market. When you purchase, when you want to develop AND gate, NAND gate, you usually purchase this chip, and usually one single chip contains 4 of these gates, sometimes with 2 inputs, and sometimes 6 like this for NOT gate, because the inputs for each gate is only 1. Then sometimes when the gate contains multiple inputs, then it contains less gate. For example, like this one, the IC 7430. This is a NAND gate, with having how many? 1, 2, 3, 4, 5, 6, 7, 8 inputs. Then here we have 2 NAND gates at 7420. Each NAND gate has 4. 1, 2, 3, 4, 5. Has 4 inputs. So these are some example of logic chips. So in terms of the integration level of the IC itself, when the easiest, the smallest integration is called a small scale integration. So each single chip only contains 1 to maximum 10 gates, like shown in the previous examples. So this is introduced in the late 1960s. All this integration level refers to the microelectronic fabrication technique. So when you introduce more gates, so more dense electronics within a single square area, then we call it a medium scale integration, MSI. This is introduced in the late 1960s. And medium scale integration can contain 10 to up to 100 gates. Then when you integrate further, more and more gates into the wafer, into the silicon wafer, then we up until 100 to until 10,000 gates, then it becomes large scale integration. Then in very large scale integration, VLSI, this is introduced in the late 1970s. It contains more than 10,000 gates per single chip. And then in the late 1980s, for example, people introduced what we call as ULSI, ultra large scale integration. Large scale. So this contain even more than 100,000 gates. This is usually used for transistor or for microprocessor or something like that. Yeah. Okay, so logical functions can be expressed in several ways. truth table. So truth table is you draw the table and then you write down the possibility of the inputs. For example, if it contains two inputs, so when both input are false, 0, 0, one input is true, 0, 1 or 1, 0, and then when all inputs are true, 1, 1, then the corresponding output values. So that's what we call as truth table. We can also express logical function in terms of logical expression. So logical expression is A dot B is basically N, yeah? A and B. So if it is or A, B, multiplication is OR. OR is positive, plus addition. A plus B is addition, while N is expressed using multiplication operator. A dot B is A and B. For example, majority function output is 1 whenever this is a logical function called as majority function. That is, the output is 1 whenever majority of inputs is 1. We use 3 input majority function. So if we draw it in truth table, this will look like this. Okay, A, B, C, and the value of the output F. Yeah. So if it is majority, means that it has to be odd. The input has to be odd. Yeah, 3 or 5, for example. If we have only 2, then we cannot have majority. 1, 0 or 0, 1, no majority. But if it is 3, then if it is 0, 1, 1, then we know that majority is 1. So here, when it is 0, 0, 0, the majority is 0, it is 0. Then the value will be false. 0, 0, 1, so majority of the inputs are false, then the output will be false as well, or 0. 0, 1, 0, similarly, the output will be 0. And then 1, 0, 0 here, also the majority are false, of the inputs are false, so means that the output will be also 0. But when it is 0, 1, 1, or 1, 0, 1, or 1, 1, 0, or 1, 1, 1, then the majority of the inputs are 1, then the output will be 1. In terms of, when we express it in logical expression, this function can be obtained using this logical expression form. Yeah, F, the value here equals to A and B, or B and C, or A and C. Okay, so let's try checking it. For example, this is in graphical form. Okay, let's say first possibility, when it is 0, 0, 0. Yeah, let's say A is 0, B is 0, C is 0. This is N value, right? Then the value here will be 0. This will also be 0. This is equal to A and B, right? A and B is 0. This is B and C. The second part is also 0. This is A and C will also be 0. 0 or 0 or 0 equals to 0. So this is the first possibility. Yeah, the first possibility. Yeah. Okay. Now let's second possibility. 0, 0, 1. So A is 0, B is 0, C is 0. So A and B will be 0. B and C will be also 0. A and C will also be 0. So this 0 or 0 or 0 becomes also 0. So this is second possibility. Yeah, second possibility, 0, 0, 1. The result will also be 0. Okay. So then let's have the third possibility, 0, 1, 0, 0, 1, 0. 0 here, the first AND gate, 0 and 1 equals to 0. 1 and 0 equals to 0. 0 and 0 equals to 0, and 0 or 0 or 0 equals to 0. So this is the third possibility. This is check, yeah, according to this table. Then fourth possibility is 0, 1, 1. 0 and 1, this one becomes 0. 1 and 1, this becomes 0. 0 and 1, this becomes 0. 0 or 1 or 0, the value is 1. So this is also correct. 0, 1, 1, the majority is 1. Majority of the inputs are 1. So that's why the value is also 1. Etc. etc. So you can check using this graphical format. Yeah, then you put input and check the output of each of the gate one by one, and to get the overall, the final output value. This is how we get into that. So the logical equivalence will be so all the three circuits in this shown in this slide implement f, yeah, the output equals to a and b function, yeah, a and b function, yeah. A, this is of course the basic gate, n, yeah, a and b, yeah. So here, so what is the truth value of n, the sorry, the truth table of n. So if we have here f, so a, b, so if we have 0 0, this will be 0, 0 1 it is 0, 1 0 it is 0, 1 1 it is 0, yeah. So for a it's like that. What about b? B is made from two NOT gates and a single NOR gate, NOR, not OR. So when it is 0, it is 0, this becomes 1 and 1, this becomes 0, right? Because NOT OR. So this basically, NOR is a combination of NOT and OR gate. So this is correct. So this is this first one. What about then if it is 0 1? So this will be 1, this will be 0, 1 nor 0, this also will become 0. This is this second one, yeah. Then the third one, let's say 1 0 1 0. So it will 1 0, this will be 0, this will be 1, 0 nor 1 also becomes 0, similar. Then finally, if it is 1 1, so nobody of you remind me that this is wrong. So apparently everybody is sleeping also. 1 1 supposed to be
1 1 supposed to be 1, sir.
1, yeah, yeah. Remind me. Yeah. Okay. So let's see here. Let's check in. So if it is 1 1, does this begin 0 0 0 0 0 or 0 is 1? 0 or 0 is 0. But if it is NOR, then it is inverted to become 1. So this is correct. Yeah, this represents an AND gate as well. A more complex one will be like this. So this is made using two NOT gates, 1 2 3, three OR gates, this one, and two AND gates. So let's see. Let's check. Yeah. So if this is 0 and 0, so this will be 0 and 0 as well. So this becomes 0 or 0. It is 0. Okay. So this becomes 0 and this is 0. So this becomes 1. 0 or 1, this is also 0. Yeah, this is 1. Yeah. So this becomes n. This is 0.
0.
And this part, this is 0 and this is 0. So this becomes 1. 1 or 0 is 1. So 0 and 1 is this is what, or n, yeah. So 0 and 1 becomes 0. Yeah. Etc. Please, because it is very long. If we have to check all the 4 possibility, then we take some time. But you can check. So this is of course not efficient, but it means what we are showing here is that we can implement the same logical function using various different possibility of circuit. Okay, that is what the point of this slide. Yeah. So there is what do you call it in bahasa Indonesia? There are many ways to go to Rome. Yeah. So how to prove the logical equivalence of two circuits? For example, in the previous slide, how can we prove? Yeah, one way is of course to check the truth table. They should provide the same truth table. However, that will take some time. We can also derive the logical expression for the output of each of the circuit. So that then if they end up the same logical expression, after we simplify the logical expression, then we know that they are equivalent. For example, so that these two expressions are equivalent, one way is to use the truth table, as we have mentioned. So for every combination of inputs, if both expressions yield the same output, then they are equivalent. Yeah, so like we have tried in the previous example. Good for logical expression with small number of variables. So for if If the inputs are only 2, then it is quite simple. But if the inputs are quite many, then it gets more complicated. What we can do is we can use Boolean identities to make it quicker, yeah, to check the equivalence. So for example, here, derivation of logical expression from a circuit trace from the input towards the output, then we write down intermediate logical expression along the path. So for example, here, so this is basically the AND gate expression, right? And the previous slide. So here become A plus B, yeah, A or B, yeah, not plus, but this is logical Boolean algebra. Plus means or, yeah, this is A or B. So this one is A or not B, okay, because there is a not gate here, so this becomes not B, and which we express it with an upper bar, a line above the symbol. So this is A or not B. This become in the lower part here not A or B. So this one becomes A or B and, yeah, because this is an AND gate multiplied, right? And A or not B. So this, the eventual output becomes A or B and A or not B and not A or B. Okay, like this one. Okay, be careful with the parentheses. So from here, then you can have this, yeah, 0, 0. If this is a simplified form, A and B, yeah, is 0, 0, 0, and then the final one is 1. So if you use this part, this the other logical expression derived from this larger combination of multiple gates. So A or B will be, this is 0, A or not B will be also 0, then not A or B will be also 0. So 0 and 0 and 0 becomes 0. Similarly with this is only true if the inputs are both 1. Yeah. So 1 or 1 is 1. 1 or not 1 is also 1. Not 1 or 1 is also 1. So 1 and 1 and 1 becomes 1. So the two circuits are equivalent. Both are basically an AND gate circuit. So when we want to simplify logical expression, we can use these Boolean identities. Yeah. Where the first algebra, yeah, identity formula is called for the n version. Whenever any kind of expression is multiplied is end with 1, then it will the result will be that value, yeah, the value of that input x here, x and 1 equals to x. So for example, if x is 0, then 0 and 1 will be equal to 0. If it is 1, 1 and 1 will be also equal to 1, the value of x itself. In our version, it is with 0. So x or 0 will be equal to the x value. Okay. So if it is x is 0, 0 or 0 is equals to 0. If x were 1, 1 or 0 equals to 1, right? The value of x. Complements means when it is being operated with the not of that input value. In the n version, if x is n, that is also operated with n gate with its inversion with not x, then the value will be equals to 0. For example, if x were 1, 1 and not 1, or 1 and 0 will be equals to 0. In the OR version, it is the result will be 1. 1 or not 1, or 1 or 0 will be equals to 1. So always 1. If it is 0, 0 or not 0, or 0 or 1 will be equals to 1. Commutative in n first is valid for both n and or. Yeah, x and y equals to y and x. X or y also equals to y or x. There's also distribution formula for n version. X and y or z equals to x and y or x and z. X or y and z also equals to x or y and x or z. Okay, so for both versions. idempotent identity. So this is when the input value is operated with itself. So x and x will be equals to x. So if it is 0, the result will be also 0. If it is 1, the result will be also 1. Similarly, with OR version, x or x will be equals to x. So x, for example, if it were 0, 0 or 0 will be equal to 0. 1 or 1 will be equal to 1. Null identity if that input is operated against 0. So this is basically the complement, yeah, of identity, Boolean identity here, null. So if in the n version, x and 0 will be equal to 0. In the OR version, x or 1 will always be equals to 1. And then we have involution, yeah, involution version. This is if we have double negation, the not of not x, that will be equals to x. In our version, there is no version of it. Absorption is x and x or y will be equals to x. Or in the OR version, x or x and y will be also equals to x. So will be equal to the outer value. Associative is x and y and z equals to x and y and z, yeah, something like that. Or x or y or z equals to x or y or z. So basically, this is removing the parenthesis form. Then this is one of the famous identity in the Boolean algebra, the De Morgan. It's very useful to simplify any logical expression. Yeah, the Morgan logical identity. Not of x and y will be equals to not x or not y. Not of x or y will be equals to not x and not y. Yeah, this is the De Morgan identity. Okay, I think that will be all for today. We will continue in the next session.